And now I want to talk about spectroscopy, chapter 4. And spectroscopy is extraordinarily important. As I said, it was only a small section in the 5th edition of Chasen and Macmillan, and now they've devoted an entire chapter to it, as I think it certainly deserves. But spectroscopy is basically studying the light that is being emitted from these very, very hot objects. What can we learn about the chemical composition of these objects? What can we learn about the speed in which these objects happen to be moving? These are things that we can get from some of the spectroscopic analysis. So in order to understand the spectrum, at least the visible part of the spectrum, and you've all observed this, that if you take a prism and you pass light through the prism, if it's white light, it will be broken up into a series of colors, a rainbow series of colors, and we'll get the red, orange, yellow, green, blue, indigo, and violet that's characteristic of the rainbow. And if I put these glasses on, my cheap little glasses here, you can see this on my face. When I look at the lights in my room, I see this rainbow, because this is a diffraction grating that's on here, and that does the same thing as a prism. When the light passes through these lenses here, these very cheap plastic lenses, the light is actually winds up being refracted, and we actually get this this rainbow effect. Same kind of thing. Now when we look at the spectrum, if we're looking at a light bulb, we get what is known as a continuous spectrum. So when I look at the light bulb through here, what I see are bands of color. So I'll see a band of red, sort of blending into a band of orange, blending into a band of yellow, a band of green. These are not sharp, distinct lines, but it's just a gradation of color going from red on one end to violet on the other end. So it's you know, I'm showing a line here, but you just have to understand that what I'm really saying is that it's red, and then it changes to orange out here, and then it changes to yellow, and then it changes to green, and then it changes to blue, and then it's indigo, and then it's violet all the way out here. So we have these all these colors, but they're just blending. One is blending into the next one over, and we call this a continuum, or a continuous spectrum. Now, you'll see this in a light bulb, and you'll also see this in the light that comes from the sun. You've got a lot of things going on, and so there are a number of elements that are being excited in the sun. In the light bulb, there's a lot of things that are going on as well, and we're not actually seeing the light that we see from the light bulb, for reasons that I'm not going to go into right now, does not give us the kind of spectrum that we can actually use to do the kind of analysis that I'm going to be talking about very soon. So in order to do that kind of analysis, we need not to get a continuous spectrum, but we need to get what is known as a line spectrum. So there's something called Kirchhoff's laws that I want to introduce right now. In Kirchhoff's laws, which I'm going to tell you about, explain what kinds of things give us a line spectrum and what kind of things give us a continuous spectrum. And we'll talk about what's actually happening at the atomic level, or actually subatomic level, that's causing this to occur. So Kirchhoff's laws, and there are 3 of them. The first one is that a luminous solid or a liquid or a very dense gas produces light at all wavelengths. So if I've got a solid, a liquid, or a dense gas, and I heat it up to the point where it becomes luminous, or I apply electricity or whatever energy into it to make it start to glow, what the spectrum, if I actually put it through a prism or my diffraction grating, what I'm going to see is this continuous spectrum that we talked about previously. So that's one, continuous spectrum. Now if I take a gas, and it's a low density hot gas, what I'm going to see, so it's a thin gas, it's not something that's very, very concentrated. I'm probably going to put that gas into a tube, and I'm going to partially evacuate the tube so that it's less than an atmospheric pressure. I'll pull it down to maybe 1/100th of an atmosphere, and what I will then have is not very, very many gas molecules, and I could actually show this to you. I've got a tube where I actually demonstrate this. Unfortunately, it won't show up really well in the video, so that's why I'm not doing this. But for instance, if I were to suck the air out of a tube, which I can do with my vacuum pump that I have nearby, I could actually put an electrical discharge through the tube and get the remaining gas that's in the tube to glow. And if we were to actually look at the spectrum of that gas, we would find that it was no longer a continuous spectrum, but it would give us what's called a line spectrum. So it would be basically a black area where we would see bands, not bands, but actually lines of light. And they're not distributed necessarily like this. It depends on what element happens to be present. But every element will actually give a characteristic. If we're dealing with gases, or even if we're dealing with, we can still do this in the gas phase with elements that are normally solids at room temperature. If we heat them up to a high enough temperature, we'll still be able to see this line spectrum. So we're going to get bright lines on a dark background, not black lines on a white background, but bright colored lines, and there'll be different colors, and we can actually measure the wavelengths of these particular lines. So that would be the second law, that a low density hot gas has bright, what we call emission lines. Characteristic of its chemical composition. So that's Kirchhoff's second law. And the third law says that if we actually take a cool, thin gas, and it will absorb wavelengths from a continuous spectrum. So let's say we've got the sun in the background, and there's a cooler, again, a thin gas, it's not a very, very dense gas, in the foreground. And so, for instance, you could have actually the sun, which is the photosphere of the sun, and then surrounding that is a cooler region of space where there's cooler gases. They're not at the temperature of the surface of the sun, but some cooler gases beyond that. What's going to happen is that those cooler gases will actually absorb from the continuous spectrum. They will get excited, but they will actually absorb bands from the continuous spectrum. So the continuous spectrum will actually, which we said were these areas that might be red and orange, etc., we're actually going to see dark bands superimposed over those bright areas. So where the bright bands here are what we call emission bands, these dark bands over the bright background area are absorption bands. So that's telling us that there is a gas in front of the sun, as you know, well, it's surrounding the sun, but the light that's coming out is actually, so when we actually look at the sun, we don't just see a continuous spectrum, but we see what are called Fraunhofer lines. Fraunhofer lines, let me see, I actually have a picture of these. There's one in your book. I found the same image on the internet, however, and I think the author of the book undoubtedly took this image. I have to, since I'm using the image, I have, it says that I have to read this. It's from the National Optical Astronomy Observatory, Association of Universities for Research in in astronomy in the National Science Foundation. And this comes from the WIYN 3.5 meter telescope, which is located on Kitt Peak, that's near Tucson, Arizona. And this is an image that was produced in 1984, and it's the exact picture that's in your textbook. But as I said, I got it off the internet, and I'm going to see if I can put it up to the screen. And you can see, let me sit down here so I can see what I'm showing you. But let's see if I can get this close enough. You'll notice that you've got this continuum. You can see the red and the yellow, but you'll also notice that there are a series of dark, well, they actually look like bands rather than lines, but there's a whole series of these things that are superimposed over the lighted areas, and those represent the absorption due to specific elements that happen to be in the atmosphere of the sun, such as hydrogen and helium and other things that might be in the atmosphere of the sun. They will absorb, and you'll get those dark lines, those Fraunhofer lines. I can spell this correctly, Fraunhofer. It's an H, H-O-F. I don't know whether it's F-F-E-R or F-E-R, but something like that, Fraunhofer lines. And these are the dark absorption lines that are superimposed over the light continuous emission spectrum. Okay, in 1868, an astronomer was looking at lines in the solar spectrum that didn't correspond to any known element. And it wasn't until 1895, which is 27 years later, that element, which was unknown at the time, and it was called Helios because the element was named helium when it was actually found on the Earth. It came from the Greek word Helios, which means sun in Greek. So helium was actually found in the spectrum, in the solar spectrum, 27 years before it was ever discovered on our planet, which is kind of an interesting observation. Now, when we talk about what's actually producing these lines and this light, we have to look again at the atom, and we're going to use an older model of the atom called the Bohr model. It's not being used anymore. We use a quantum model of the atom now. But to understand this particular phenomenon, it's actually easier to picture the atom as a Bohr atom. And the Bohr atom is one that has a nucleus, as does the quantum atom as well, but the difference actually has to do with the way the electrons are arranged. So we have a nucleus, we have protons and neutrons, or in the case of hydrogen itself, just a single proton. If we're talking about protium, the lower isotope of hydrogen, just a single proton surrounded by an electron. So for hydrogen, we just have one proton and an electron. Now in the Bohr model, it's usually shown that the electron is orbiting around the proton, something like that. In the quantum model, we don't look at the electron as a discrete particle anymore, but we talk about not it having any particular location because of the Heisenberg, what is known as the Heisenberg uncertainty principle. We can't predict the location of an electron and its momentum simultaneously. So there's some uncertainty about where the electron actually is at any given point in time. And so what we do is we say that there's actually a shell. In this case, it's a spherical area, not a shell, but a spherical, there's kind of like a ball that surrounds the proton. And somewhere within this ball, if I make this a sphere now, I say that in this spherical area, there's a 90% probability of finding that particular electron within the sphere. And for other electrons, for higher elements, there are more complicated shapes that the orbital might actually have. But as I say, for the purposes of discussion now, we're just going to assume the Bohr model, and we're going to assume that the electron can be what we call at the ground state. So here's our electron, and it could be at the ground state, and we'll call this E sub 0, that's the lowest energy. It can also move up to excited states. So we can have, for instance, let's remove our hydrogen atom here, and we could have another state up here, which I'll call E1, and that's our first excited state. Electron could jump up here. It could also be at E2. It could also be at E3. And what I want you to notice is that each of these distances is becoming smaller as I go up the ladder here. E3, E4, E5, and I could have something up here which I'm going to call E infinity. And E infinity is actually the energy at which that electron is going to be ejected. I'll actually have ionized the atom. So I put enough energy in there that that electron is actually going to leave the atom entirely. It's no longer going to be bound to the atom. So if I did that with a hydrogen atom, I'd have a free proton, and I'd have this electron that's just moving on its own somewhere out in space. Would eventually be captured by some other free proton, perhaps. But basically, what we have here is the electron is at the ground state. And as I put energy in there, it's kind of like walking up steps. The electron can go up to the first step, it can go up to the second step, the third step, the fourth step, and the fifth step. What the electron can't do, any more than you could do this, is the electron cannot be between the ground state and the first excited state. In other words, it can't be on the 0.5 step, any more than you can balance yourself mid-air between the ground floor and the first step of a stairway. This is what we mean when we say that these energy levels are quantized. That is, again, there is no continuum. We talked about the continuum before. There's no continuum of energy, but there are discrete, and actually we can calculate exactly what the values are for these particular energies, but there are discrete energies that this electron can have in the hydrogen atom. Now, for larger atoms, for helium and atoms that have more electrons and their other particles, this gets very, very complicated. But it's relatively easy to explain for hydrogen, and it's a good thing too, because hydrogen, being the most abundant element in the universe, it's something that we see all the time in space, and it's a thing that astronomers are particularly interested in, hydrogen, because that's where the action is, wherever there's hydrogen. Space is mostly empty. There's a vast emptiness in space. When you see collections of hydrogen, that's where you have star-forming regions. That's where all the action is. That's where things are going to take place. So that's what you look for in deep space when you're trying to find something new. Anyway, so you're going from E0, E1, E2, E3, E4, and as I said, these things are getting smaller and smaller. So an electron, let's say an electron moves all the way up to E5. We put enough energy in there and it gets excited up to E5. Now, once it's in the E5, that's not a stable state. It's going to decay, and it's going to fall back down to lower states. So it could fall from E5 to E4, from E5 to E3, etc. But there's one particular thing that we're particularly interested in, and that's when this falls from E5 to the first excited state. Or it could fall, the electron might be been promoted up to E4, and it's going to fall back to the first excited state. So it could go from E5, let's look at these. It can go from E5 to E2. It can go from E4 to E2. It can go from E3, let's see. I didn't do this right. That's the way I labeled this thing. Let me just relabel this. I wanted to call the ground state E1. That's why it's confusing. E4, E5, and this would be E6. So we can go from E6 to E2, from E5 to E2, from E4 to E2, and from E3 to E2. And once we get to E2, then we can just drop to E1. But you'll notice that there are 1, 2, 3, 4 transitions that occur here. And each one is actually, because of the fact that these levels are not exactly the same, each one of these represents a different amount of energy. There's a greater energy going from here to here than there is going from here to here. And obviously there's going to be the greatest energy is going to be going from E6 all the way down to E2. That's going to be greater than going from E5 to E2, from E4 to E2, or E3 to E2. E3 to E2 will be the lowest energy change that you can possibly get for that particular kind of transition. Well, these things, these 1, 2, 3, 4 transitions, actually produce the hydrogen, the visible part of the hydrogen emission spectrum. Let me see if I have a picture of the hydrogen emission spectrum. Well, this is showing you what an actual hydrogen emission spectrum would look like. Let me see if I can get this into some kind of focus. So you see hydrogen there, and I don't know if you can, I don't even think you can, we can barely see the bands. Let me see if I can get close enough that I can point to them. You see, I've got my finger now over a blue band right here. I don't know if you can see that. So my finger is right over a blue line. I'll try to get a little bit closer. There's another blue line over here. There's a second blue line over here. Now let's go back in the other direction and see if we can see anything else in there. There's actually sort of a greenish line, but I don't think you can see it. And there is a red line. You don't see it on here, unfortunately. But there is a red line in there as well. It's that red line that astronomers are particularly interested in. And I was kind of hoping to be able to show it to you. But that is called the hydrogen alpha line. So this line here, the red line, which is the lowest energy transition, going from E3 to E2, this gives you the hydrogen alpha line. And this particular series of 4 visible lines, and that's all we see. We only see 4 visible lines. In your textbook, there is a hydrogen spectrum that's shown that shows you 6 lines. However, if you look at the wavelength, and I don't remember what page it's on, but if you look at the wavelength, you'll see that 2 of the lines are really not in the visible region of the spectrum, even though they're shown, they're actually shown, you can see them, but they're really not in the visible region of the spectrum. They're in the ultraviolet region. So the bands that are in the visible region are what we call Balmer, B-A-L-M-E-R. These are Balmer lines. These are the visible lines. And hydrogen alpha, the alpha line, which is the line in the red region of the spectrum, is the not weakest in terms of intensity, but the weakest in terms of energy. That's the lowest level transition. This would be the one, I think I said there was a yellow or green line in there. I think it's green. So the green line would be the one that would be going from E4 to E2. And those 2 blue lines that I showed you are E5 to E2 and E6 to E2. And those are, again, the highest energy ones. So those are shifted into the blue because blue is a higher energy than red or any of the other colors happens to be. Okay, so we've got the 4 Balmer lines, and then we could look at transitions, for instance, that go from E6 all the way down to E1, or from E5 to E1, E4 to E1. So we've got E6 to E1, E5 to E1, E4 to E1, E3 to E1, and E2 to E1. Now we count these up and we find out we have 1, 2, 3, 4, 5 lines, and these lines are going to be even greater energy than the visible lines, which is going to put them into the ultraviolet region of the spectrum. So these are UV lines, and this series is called the Lyman, L-Y-M-A-N series of lines. So we've got the Balmer lines, which are visible, the Lyman lines, which are invisible in the ultraviolet, and then we also have a set of lines that go from E6 to E3, E5 to E3, and E4 to E3. There's only 3 of those. E6 to E3, E5 to E3, and E4 to E3. So there's 3 lines here, and these are going to be in the infrared. These are the least energetic, and these are called Paschen lines. So there are the 3 series: the Paschen, the Balmer, and the Lyman. And your book makes the point of the Balmer and Lyman lines being probably most interesting for astronomers.